My name is Mike DeLaCluse. I'm the president of Lesman Instrument Company. I'd like to thank all of you for taking time out of your busy schedules to join us for how to improve your maintenance strategy with wireless sensors. Today's speaker is Michael Thevanh from Bentley, Nevada, which is a Baker Hughes GE company. Michael's been with them for over 27 years. Today in our webinar, he's going to cover some maintenance strategies, reactive, preventative, predictive. He's also going to get into how to select applicable technology for your maintenance strategy based on some asset criticality and PF interval. And then he'll look at some common applications, and then at the end we'll take your questions and answers. Michael started his career with Bentley, Nevada as a design engineer after graduating from Texas A&M University with an electrical engineering degree. His current role as a senior field application engineer has him supporting the Bentley, Nevada product line. With that, Michael, I'll turn it over to you.
Well, thank you everyone for joining the webinar. I know everyone's busy, so really appreciate the time that you have selected to join us. This morning, obviously, we only have maybe 30, 45 minutes top together, and I'll do a quick review of the 3 or 4 different maintenance strategies that's out there. And, obviously, you're not going to be an expert by the end of the webinar after 30 minutes, but we'll do a quick review. And I don't know how many people is on the phone or the background, so forgive me if it's something, this is elementary, but we'll do a quick review. And toward the end there, we'll talk about a particular technology, a wireless sensor technology that could potentially help move you from one maintenance strategy to the next and whatnot, and that potentially could help you improve your maintenance strategy. So we'll get started with just a quick review of the strategies, and then toward the end we'll talk about the new wireless sensor technology that Bentley, Nevada came up with. Maintenance strategies. There are 4 basic types of maintenance strategies out there, and we'll cover each one in a brief couple of slides afterward. You have your reactive maintenance, you got preventative, predictive, and the PCM, proactive center maintenance. So let's just say you're in a reactive maintenance strategy in your facility, your company, and whatnot, and maintenance is kind of performed after a failure or after some kind of obvious, unforeseen threat of immediate failures. The motor is smoking. You can kind of see, it's on fire. You see a fire truck there on the right, and it's basically you're literally fighting fire, on your day-to-day routine. In reactive maintenance, your machines or your assets, your pumps, your motors, your fans, whatever, typically operate in a run to failure mode. You run it to basically literally until it stops working. Functional failures. Your daily maintenance activities are kind of driven by the unforeseen problems. The assets breaking down because you really don't have any kind of detectability issues, so you can't see the impending failures. So you're literally fighting fire, literally every day. Reactive maintenance, sometimes referred to as a living life at the bottom of the P to F curve. P is the potential failures, and F is the functional failure of the asset. I have a slide in the next few slides. We talk about a little bit about that. It's planned run to failures. In other words, I'm going to run this asset until it fails, basically. Maintenance dictated by the unpredictable machine behavior. You're responding to emergencies only. You're not doing any preventive or predictive type of maintenance. And reactive maintenance is probably the most expensive type of maintenance. If you take into consideration, for example, the unplanned outage cost, right? If you're fighting fire every day, you have potentially a lot of unplanned outages, and the production loss of the cost associated with that unplanned outage. If you take that into account, reactive maintenance is probably the most expensive type of maintenance out there today. So, as we go through these strategies, the types, be thinking of where you are today. And then toward the end, we're talking about potentially applying a sensor technology to help you improve your maintenance strategies. So the next strategy in the maintenance world is basically called preventive maintenance, right? You have reactive, in other words, you're in reactive mode, fighting fire constantly. Now, preventive maintenance is a step up. Maintenance usually tasks are conducted at a regular or some kind of scheduled intervals, and that the intervals can be based on some kind of statistical averages or some kind of anticipated run time to avoid failures. The intervals may be be based on a calorie base or operating time. In other words, okay, this turbine is we're going to bring it down after X number of hours of operating time. So we're going to do inspection. Preventive maintenance can include inspection, service, and or replacements of the part. Preventive maintenance is conducted to keep basically equipment working or extend the life of the equipment. In other words, you change the oil in your car every 3,000 miles, regardless of the condition of how you drive, regardless of the condition of the oil. So you do that to extend the life of your engine. Preventive maintenance is time-based. Also, it can be based on OEM recommendation as well. Like GE has their gas turbines. They will recommend to the customer, after X number of hours of runtime, you need to take it down, do inspections on these pieces of equipment. PM can be, either intrusive or non-intrusive. So it could be both. Obviously, preventive maintenance can be more effective than your reactive maintenance. Remember, your PM versus fighting fire, you kind of have some kind of preventive maintenance. In other words, for example, you take the pump, the fans, whatever out, change the bearing after every 5, 6 years. So that they'll help it run longer, even though the bearing may not need to be changed, but you're still doing it because it's based on time. Preventive maintenance basically improve production, basically, reduce unplanned downtime because you're replacing, these components based on time. You can mitigate wear and tears in equipment by keeping it clean and lubricated. You change your oil every 3,000 miles. You can certainly keep the oil clean and lubricated. And reduce maintenance and repair costs by eliminating, emergency repair services. So that's preventive maintenance. It's kind of like a step up from your reactive maintenance. Some of the shortcomings with PM, preventive maintenance, is not based on failure modes. It's not based on the condition of the assets. It's based on time or some kind of, recommendations. With PM, preventive maintenance, you can certainly introduce infant mortality failures. In other words, you're start and stop the motor, or you're taking them apart on a regular basis, and you may not put them back correctly. So you could potentially introduce failures that way as well. It's time-based. It's not condition-based. In other words, again, referring back to a lot of people change that oil every 3,000 miles, regardless of how the oil looks. And the asset unavailability during outage can sometimes outweigh the availability gains as well. It can be intrusive, PM tasks, and you may reduce the asset life cycle by start and stop it on too many times. You start and stop the motor too many times, it could potentially reduce the life cycle of the asset. PM, preventive maintenance, do not completely reduce the need for the reactive maintenance. You can see the picture done right there as they replace filter cartridge every 6 months. Regardless of whether it's dirty or not, you're replacing it. The next maintenance strategy, you remember you got reactive, preventive, is predictive maintenance. This is maintenance based on the actual asset conditions of the assets. Under maybe the non-invasive test or operating and condition measurements. You apply, this also referred to as a condition-based maintenance. This one I can think of. My daughter's car has like an oil sensors. Instead of changing the oil every 3,000 miles, that oil sensors is in the, it's looking at the condition of how the car is being driven and the condition of the oil, and then they will flag, say, okay, after, you have 20% of life and of the oil is available. So that's more a predictive mode or vibration monitoring system. So you can put a accelerometers or some type of measurements on the machines to do more of a predictive PDM, evaluate machinery via instrumentations. You typically employ some type of condition monitoring technology, whether it's vibration, thermography, infrared. Those condition monitoring technology would be employed. You monitor health of the asset in like a PTF curve cycle. You could potentially, have some early detection of failures, and then that can drive planning and scheduling. For example, if you employ a condition monitoring such as vibration, the vibration maybe allow you to see the condition of the bearing on the motors, the pumps, and whatnot. And then, with some of the technology, it allows you to see pretty early detections of bearing failures. And then you could have, planned and scheduled outage versus a unplanned outage in your reactive mode. It integrates other reliability tools, your Six Sigma, your root cause analysis into that condition monitoring as well. This maintenance strategy, predictive maintenance, you have less downtime during maintenance, less expensive recurring maintenance, and obviously it costs less than your preventive maintenance or reactive maintenance. So this is where a lot of our customers is at. They have some form of a PDM program. For example, in the vibration world, the customer have a portable instrument that he or she, the data regularly go out there, collects data, on the asset, on the condition of the asset. So the last one is proactive center maintenance. This is where mainly your top 5% quartile of the top performer customers are at the PCM level. Proactive centered maintenance program continues to maintain, basically optimizations. It's based on feedbacks. Basically, this is a key. You have a loop, so you're kind of looking at your failure costs, failure modes, repair, the preventive. You take into considerations all the belows and have feedback loops and continue to enhance the maintenance. So it'd be better. PCM, take the holistic approach of maintenance. You do right maintenance on the right asset at the right time. In other words, you're only taking this asset down. This as an example of bearing, when you take this motor pumps down, when you see the condition of the bearing has deteriorated, and you have planned outages, you have bearing in play, new bearings already ordered in place, so your downtime would be much less. This maintenance strategy employs both the preventive, predictive, and the reactive strategies, and it's continuing being optimized, like I say, based on feedback from the root cause failure analysis, the PDM routines, and so forth. So it's a feedback loop basically. In the long run, a PCM strategy may cost more to implement at the beginning, but really offers the lowest maintenance spend. So those are the four basics, maintenance strategy, and as we go through this, you can kind of be thinking where you are or where your facility is at in terms of different strategies here. This slide offers a little bit of what I just to kind of summarize what I discussed. You can kind of see the bar graph here on the left in terms of maintenance strategies, reactive, preventive, and predictive, and so forth, and the cost associated with it. The reactive, cost is much higher than your PCM, maintenance strategies. And you go to the right here. Notice that each, maintenance strategy has a plateau. In other words, on the x-axis, you can continue to spend as much money as you want, but you're not going to get a whole lot of effectiveness, availability outcome of it once you reach a plateau. So the only way you can improve, in other words, reduce maintenance cost expenditure, in other words, on the x-axis moving to the left, and increase effectiveness on the y-axis going upward, is to move from one maintenance strategy to the next. In other words, if you're in a reactive mode today, the only way to make significant enhancement would be, reduce costs and increase effectiveness, but move from reactive maybe to a predictive mode. that's really the only way to make significant enhancement in your, maintenance and effectiveness. And I mentioned the PTF here. The P is potential failures, detections, and the F is functional failure. The X-axis is the time. The time can be in seconds, minute, days, months, years. It's basically, and then these are the condition monitoring technologies that could potentially help you detect, before it gets to the functional failures. Just quickly summarize the maintenance strategies and review basically the four strategies, reactive, preventive, predictive, and proactive maintenance. If again, like I mentioned earlier, how can I, if I'm in reactive mode today in my facility, is basically I'm fighting fire on a day-to-day basis. How can I move to something better, more of a condition-based, to a predictive type of maintenance strategies here? Possible thing could be, you employ a condition monitoring technology, and one of the things that you could potentially do is maybe condition monitoring using vibration. The vibration could be permanently install sensors that goes to a transmitter, and they go to your DCS, or you can have some kind of monitoring system, or Bentley Nevada just came out with a wireless condition monitoring system, vibration monitoring system called Ranger Pro, and that's what I'm going to be covering the next couple of 5-10 minutes. The Ranger Pro is the name of the product that Bentley Nevada recently came out with. This slide's kind of give you a quick pros and cons comparison between a wired system versus a wireless. A wired, what I mean by that is that you have an accelerometer or proximity probe or whatever mounting on the machine, and then you would run a wire from that sensors to a local junction box, or to a transmitter, or to some kind of condition, a monitoring system like the Bentley 2300 and whatnot. And then you could certainly have protection to trip the machine and whatnot. And wireless, on the other hand, the pros would be very easy to deploy, very fast, fast to expand, very cost effective, and truly wireless. In other words, you don't have to pull cabling from the sensors to your control room and whatnot. So the details of the wireless sensors for the Ranger Pro. On the right here, you have a sensor, the Ranger Pro sensor, that's fully assembled. You can kind of see the height of it is about maybe 3.5 inches by the diameter. The width is basically 1.6 inches. So this is the fully assembled wireless sensors. Notice there's no wired. It's battery operated. So exploded view of the sensors, taken apart from this, fully assembled here. You have a base, basically, of the Ranger Pro. Built into this base, you have an option of either a single or triaxial accelerometer, as well as a temperature measurement device. In other words, it will measure temperature and vibrations from this base. The triaxial accelerometer is convenience because a lot of our customers now, sometimes when they do a portable data collection, they take the measurement at 3 axis, let's say at an outboard bearing of a motor. They take the measurement as horizontal, vertical, and axial, right? So that's 3 axis. With this sensor, you can mount it, at one location, and you get the actual 3 measurements, X, Y, Z, from that location. So that's convenience, as well as temperature. So moving from the base, you have a battery. That's a D-size battery. It's a lithium thionyl D-size battery. It's 3.6 volt high density battery. And we went with, instead of customized battery, we actually went with the off-the-shelf battery. So you can buy this battery from Amazon, Battery Plus, LI Electronics, or whoever sells, D-size battery. And the battery typically costs about $19, $20 a piece. And based on the scan time, a lot of customers would ask, how long is this battery will last me? If you get data, 3 or 4 times a day, it probably lasts you maybe 3 to 5 years before you have to change out the battery. So you put the battery into the base, you hold it down with the base, the battery holder here, you twist, you screw it in here and tighten it down. And then you basically, place in the E module, I call it. This is where the electronics, the antenna, the radios are all built into this E modules. And then this is ring here, holds everything in place. So just fully assemble, and this is what it looks like once it's fully assembled. You mount it on the machine and start collecting data. Quickly go over the specification of the sensors. Is rated for Class 1, Division 1. So notice that, a lot of the plants are Class 1, Div 2, but this sensor is actually rated for Class 1, Div 1. It's truly wireless. There's no wire at all whatsoever. It's mounted, we have a stud mount here, a magnet mount, or epoxy mount. So underneath this sensor here, there's a threaded hole, so you can have an adapter that goes to anything from quarter 28 metrics, like a M6. So any adapter that you need, we have it. And each axis of the vibration, let's say you have 3 axes, you will provide both velocity and accelerations and temperature, right? So not only you get acceleration that you use to detect bearing issues, high frequency stuff, you can look at velocity signal, which is, rotor related issues, running speed of the machine. So you have the best of both worlds, acceleration and velocity at X, Y, Z axis. It uses, a self-healing IC100 wireless protocol. The battery is not rechargeable, so replaceable lithium battery. It's IP67 rated, and right now the temperature goes from -40 to 85 degrees C. The upper end here of 85 degrees C is really due to the limitation of the battery. We're looking at maybe potentially higher temperature battery as well. So right now we can only look up to 85 C. The range, line of sight, in other words, you have a sensor here installed. It can talk to the next sensor. It could be up to 200 meter line of sight. In other words, you can see, if I can stand where the sensor is, and I can see the next sensor. 200 meter, that's probably like a couple of football fields. But in the industrial environment, we're looking at, safely anywhere 75 to 100 meters of range. It has built-in 128-bit encryptions. You can talk to Modbus, to your DCS, and so forth. Infrastructure-wise, you would have to put in this, right now, a gateway infrastructure. In other words, you have access point. Notice this picture right here. This access point is typically mounted out in the field, and this is where the sensors communicate to. So the sensor communicate wirelessly to this access point out in the field. So you can have, if you have a big area, you can have multiple access points mounted out in the field. The access point then connect up to the gateway, and the gateway communicates to a Modbus OPC to your DCS or plant historian, or you can go to our software called System 1, so you can do diagnostic, waveform and spectrum and things like that. Right now, GE Bentley Nevada does not have our own gateway system, so we use either Yokogawa or Honeywell as the infrastructure. The sensor themselves are, can form a mesh type of network. What I mean by that is it can communicate through other sensors in a mesh type of network and hop back. So then, you can get back to the gateway. This is a graphical map of, the install system. You have a access, the device manager gateway, and you have one access point, and you kind of see all these sensors communicate to this access point. And here's the vibration, the temperature and the vibrations coming in from these sensors. And it has maps basically that shows you the connectivity from these sensors, the signal strength, and all of that. So, and this is a Honeywell configuration screen. And this is a graphical view of System 1, and you can kind of see the temperature vibrations coming in from the sensors. So that's kind of the end of my presentations.
Michael, thank you very much for your presentation. If there are any specific application questions, feel free to give us a call at 800-9-LESMAN or 800-953-7626. If you don't know your account manager, feel free to ask for me, Mike DeLaCluse, and I'll make sure that you get taken care of. You can also reach out to me at my email, which is miked@lesman.com. If you want to know more about the technologies we supply, all of our webinars are posted both on our website and on our Lesman Instrument Company YouTube channel. If there are topics that you'd like us to cover in our webinars, please send me an email with the subject. We have access to lots of product and process specialists, so let me know what you'd like to learn about, and we should be able to get an expert to cover it.